Well, thank you very much for the introduction. It's a pleasure being here. Actually, I think my first visit to UCLA was in 1984, a long time ago. So it's a great pleasure to be back. All right, so I'm going to talk about quantum Wasserstein, a sort of quantum Wasserstein distance, and the observability problem for quantum dynamics. And I should say right away that this is joint work with Thierry Paul, but actually it is answering a question which was raised by Claude Bardos some time ago. All right, so let me go right away in the specifics of the talk. So what I mean by quantum dynamics, this is going to be very much a PDE talk, right? So maybe I should apologize for this. I don't know. So what I mean by quantum dynamics is going to be the dynamics defined by either the Schrödinger equation, which is written here. So here you see that you have a quantum Hamiltonian that's taken mass equal to 1. And I'm looking at a particle which is pushed or subject to the force deriving from a potential V that's independent of time. And here I've written everything in terms of a wave function psi of t and x, satisfying the normalization condition as always. But as a matter of fact, it will be more natural to think about the von Neumann equation for a density operator, time-dependent density operator. So what I mean by a density operator here is a self-adjoint non-negative operator on L2 of Rd whose trace is equal to 1. Okay? So here we'll always assume that the potential V is real valued. It's a real valued function such that curly H, which is the quantum Hamiltonian here, has a self-adjoint extension to L2. And this is a problem which has been studied a long time ago in the early 50s, possibly late 40s, by Kato in particular. So we have a very good knowledge of the V's for which this is true. And when that is the case, then by Stone's theorem, the exponential of minus IT curly H divided by H bar is a unitary group on Gothic H, which is L2 of Rd. And psi times t is given in terms of psi times 0 by this formula here. And R of t is given in terms of R of 0 by conjugation with the same dynamics. Okay? Good. So much for quantum dynamics. And now let me say a few words about observability and observing the solution of a PDE. And let me start right away with an example which everyone knows. This example has nothing to do with quantum mechanics, but is perhaps the best known of the first observation problem which you encounter when you study mathematics, which is the analytic continuation principle. So if you take a domain in the complex plane, call it U, and take an open set, non-empty open set included in U, and now take a distribution on U, which is in the null space of the Cauchy-Riemann operator, d bar. So d bar f equals 0. So in other words, f by elliptic regularity, we know it's a holomorphic function, and we know by analytic continuation that if f is identically 0 on the open set omega, then it's going to be equal to 0 on U, because U is domain, therefore connected, and you have analytic continuation. So in some sense, you see that observing, you should think of omega is a part of the domain where you can actually monitor the solution of this particular PDE, right? So you observe the solution in omega, you see that it is equal to 0, and you infer that it's going to be equal to 0 everywhere, right? So there is another problem, which is about, the question is whether there exists a constant, say, depending only on capital omega and capital U, such that for holomorphic functions on U, you would like to know whether f in uniform norm is going to be controlled on U from the knowledge of its sup norm on omega. Okay, that's obviously this property implies the previous one, but it's slightly different in the sense that it's you have an effective constant by opposition with by contrast with this case here where you don't claim that there exists such a constant. Okay. All right. So okay. So if we apply this to quantum dynamics, you will say that a class curly K of quantum states, which I can consider at time t equals 0, is going to be observable in omega, which is going to be a subdomain of RD, which is going to be open, and you want it observable in time t for the dynamics U of t, if there exists an observation constant, positive, such that, the L2 norm in time and space of the solution in omega cross 0t dominates the global L2 norm. And because the global L2 norm is time invariant, you can take it from the initial data and say in the case where psi is a bona fide wave function, in other words, a state, and this is equal to 1. Okay, so the question is whether such a constant exists for all initial pure state in your class curly K. And you can pose the same question, you can ask the same question for Neumann dynamics. So you would like to know that for all initial density operators are initial in curly K, then C obs, there exists a positive constant C obs, such that the integral from 0 to t of, so what is going to replace the L2 norm of psi in omega is going to be really the trace of R of t multiplied by the indicator that x is in omega, right? And so you want this to dominate the trace of R at any time t, in particular at t equals 0. Okay, so that's the observation inequality here. Now, observation inequalities, people doing PDEs, they like them in control theory because of something that's known under many names, but perhaps in my community it's called the Hilbert uniqueness method for Schrödinger, but the Hilbert uniqueness method, which I think initially was formulated by Jacques Rillons for the problem that was not the Schrödinger equation, but was the wave equation. But there were earlier, I think, results for the Schrödinger equation, which there is a reference in this paper with Thierry Paul on which this talk is based. Anyway, so let me briefly explain how it works for those who don't know it. Okay, so I return to this self-adjoint Hamiltonian. Oh, sorry, it should be curly H. No, it's not so curly. And the H bar has disappeared. I'm sorry.
Natural units.
Natural units, thank you. So this is your self-adjoint Hamiltonian, minus 1/2 of delta x plus Laplacian plus v of x, right? And you have two problems that you want to consider. The first one is the control problem, meaning that you look at the solution of I dt phi equals h phi, and you allow yourself to put a control which is going to be a right-hand side, which you choose, an f. But the only thing is that this source term has to be concentrated and has been localized in 0t cross little omega. And you want that this guy is chosen so that at time t equal capital T, the solution of this equation here is driven to be equal to 0. Okay? That's the definition of the control problem. Can you find an f such that by acting, in other words, you're acting on the system only during a time interval t, and you're acting only in some part of the domain, which is little omega, and you want at that time, capital T, this is equal to 0. There's another problem, which is the observability problem, which is a Cauchy problem. So you start from psi t equals 0, psi initial, and you solve the Schrödinger equation without any right-hand side. And so you have, in this way, two natural operators to look at. The first one is the control problem, as you have a control operator, meaning that if you give the control, in other words, the function f, this source term, which is in L2 of 0t cross little omega, you associate minus I times phi at t equals 0. So in other words, it's minus I times the initial data for this problem here. And there is the observation operator, which is this guy here. So you start from your initial data for the second problem, so it's the Schrödinger equation here, and you look at the restriction of the solution on omega cross 0t, right? Which is going to be a function in L2 of 0t cross omega. Now, you see immediately that this space is equal to this one, this space is equal to this one, so any reasonable mathematician would suspect that these two operators, they are adjoint to each other, and this is indeed what happens, and this you can check by the simple series of integration by parts, which I let you check, and you see indeed that the control operator as adjoint equal to the observation operator. And if you look in your favorite book in functional analysis, it tells you that the range of C, if you take the closure of the range of C, the control operator, this is going to be the orthogonal of the null space of the observation operator. Okay, so that's basic functional analysis. What is a little more interesting is that if there exists an observation constant, positive observation constant, in the sense of this inequality here, right? If there exists such a constant, then in fact, the range here is going to be closed, and therefore the range of C is going to be the orthogonal of the null space of the observation.
Is it equivalent?
Sorry?
Is it equivalent to being to the
Yeah, sure, of course, yes. But I mean, the thing is that, the way it's used, of course. Yes, you're right, it's equivalent, yes. But the way it's used is that if you have a constant, then you know that the range of C is going to be the null space of the orthogonal of null space of the observation operator. Okay? Good. All right, so, well, I mean, of course, then this tells you that it's interesting for people who are want to control an equation. It's interesting to understand what are the domains. These how can you choose this little omega so as to be able to either control the solution or observe it? And you understand that this is the same problem. Okay, so in 1992, these gentlemen, Claude Bardos, Gilles Lebeau, and Jeff Rausch, they provided a necessary and sufficient condition for controllability or observability of solutions of, well, it's not going to be for the Schrödinger equation. They did it for the wave equation in a bounded domain. And the difficulty in their paper, the real difficulty in this paper, is that they wanted to control the wave equation by acting on a subset of the boundary of the domain, which is supposed to be smooth. Now, the proof, their proof uses microlocal analysis, and rather heavy-duty microlocal analysis. It's based on a beautiful initial observation by someone from here, by Jim Ralston, which appeared in CPAM 1969. And so, which is a very beautiful and easy to read paper. There's no less beautiful but less easy to read series of paper by Melrose and Schoestrand, which appeared also in CPAM around 1980, about the propagation of singularities in domains with boundaries. And you understand that whenever you hit the boundaries, the wavefront set could be doing strange things, and this is classified in these couple of papers by Melrose and Schoestrand. Now this is evolved into B calculus and all kinds of things, which are rather fancy. Okay, so the fact that it's the boundary is makes things harder. Okay, now here I'm going to do something much simpler, but which will avoid microlocal analysis anyway. So here, so let me try to explain this geometric condition provided or found by Bardos-Lebeau-Rauch, which implies controllability or observability for the wave equation. But here I'm going to do it in the case of the Schrödinger equation. So what you do is that you look at the flow of the classical Hamiltonian corresponding to your quantum Hamiltonian. Quantum Hamiltonian is simply the kinetic energy plus some potential V of x, time-independent potential. Okay, so now you look at the Hamiltonian flow of the classical Hamiltonian here. So in other words, you have a capital X, capital Xi, which is the solution at time t of this set of Hamilton's equations. X dot equals dH d xi, which is nothing but xi, and xi dot is minus del V at x. And you require that capital X, capital Xi at t equals 0 is equal to little x, little xi, and this is what you define as capital X, capital Xi at t, starting from little x, little xi, right? So the geometry condition proposed by Bardos, Lebeau, and Rauch is a condition that is going to be satisfied by a triple k, omega, and t, where k is going to be a compact subset of phase space. So it's a compact subset of R2D, right? So these are classical coordinates. Omega is an open subset of RD, so it's a set of positions, right? It's where you're going to look at your solution. It's where you're going to observe your solution. And capital T is a time during which you are going to observe the solution. And the geometry condition is that if you start from any phase space point in your compact set capital K, there exists a time between 0 and capital T where the trajectory of the classical system here is going to enter the domain, the spatial domain omega. So in other words, there exists a t between 0 and capital T such that capital X of t, x, and xi belongs to omega starting from an x and xi in K, right? So that's a geometry condition. Okay, now what it means really, let me illustrate this with a...
What was omega again?
Sorry?
What was omega exactly?
Omega is an open subset of RD. It's a space of positions only, right? It's a d-dimensional open set, right? So it's going to be the set on which you observe your quantum dynamics, okay?
But you could take moment as well, if you wish.
You could take moments, but for some, yeah, sure, of course. You could take, but not thought about that, right? Yeah, but yeah, sure. But you look at, here we're going to look at position. Well, you know, I mean, physically, for people wanting to control a wave equation, they put some kind of mechanism somewhere in the domain, and they you know, I mean, that's how it works. How you observe momentum is, I wouldn't know how to do it, right? Okay, so let me give an example of this geometric condition where you see exactly how it works. But unfortunately, the example, if you want an example where you can see something on a picture, it has to be one-dimensional because you're in phase space, and phase space higher than one-dimensional, I don't have so much geometric intuition. So here, I'm going to look at dimension 1 and the simplest imaginable dynamics, which is a free flow, right? So V equals 0. The classical free flow is just capital X is little x plus t xi, and capital Xi is little xi, right? So here, let me take a closed rectangle K in phase space, which is here with the ordinates being Xi and the psi set will be X. So here I take a phase space rectangle and I move it by the free flow. So it's deformed into this parallelogram here, which you see. Right? And then as time goes on, you see that, for instance, I'm looking at the distortion of this phase space rectangle, this push forward this phase space rectangle by the map phi, by the free flow at time t equal 1/2. and t equals 1. So you see that, for instance, if I take this interval capital omega, it satisfies the geometry condition with c equals 1 because, well, I mean, you can see it at any time, you know, any point inside this rectangle will cross capital omega. But this is not the case of the little omega, which is here, because if you take phase space points on the bottom side of K, they stay out of the strip built on top of little omega for all time between 0 and 1. In other words, for time equal 1, the motion is not fast enough to enter the little omega, right? Okay, so not all, there are some points which are so slow that they don't enter little omega in time t equal 1. Okay, so that's essentially an example and a counterexample of a triple satisfying this geometric condition. This is the simplest of all, of course. Okay. All right, so now, yeah, quantum Wasserstein, because so far it was very much, not very much quantum Wasserstein in this business. So now, I mean, I'm going to describe something which I studied with Thierry Paul some years ago. So the idea is to define some kind of a metric, but this metric is not going to be a bona fide metric in the sense of Bourbaki or whatever Bible of mathematics you can think of, in the sense that I'm not going to compare two objects in the same set, right, which I think Bourbaki would be, or any reasonable textbook in mathematics would be doing. I really will be comparing pears and apples, right? So in other words, I want to compare a classical density, a phase space density, a probability density, with a density operator on your Hilbert space Gothic H. So how does this work? Well, the idea is to do this by mimicking the construction of the quadratic Wasserstein distance. And the first task is to define a notion of coupling, transport plan, or whatever you want to call it, between a probability density on phase space, absolutely continuous probability measure, and R2D, Borel probability measure. And you want to compare that with a density operator on Gothic H. And so a notion of coupling, a transport plan, I always say coupling for some reason. Well, it's going to be a operator valued function defined on phase space. It's an operator valued function of x and psi. This operator is going to be a self-adjoint and bounded operator on Gothic H. And I want this guy to be almost everywhere non-negative. Okay, so this is positivity condition. I give you the marginal condition is that the trace of q of x and psi should be equal to f of x and psi almost everywhere. And the integral of q of x and psi, if I integrate in x and psi, should be equal to r, which is, so these are your two marginal conditions, right? So here, the trace is like averaging over the quantum variables, and integrating in x and psi is like averaging out the classical variables. So purists might find it dangerous to be integrating operator-valued functions in L of Gothic H, which is known to be non-separable, so there might be measurability issues. But here, I remind you that F is a probability density, so in fact, this guy is going to be trace class almost everywhere, and therefore there are no such measurability issues because trace class is going to be separable, okay? Good, so with that being taken care of. Now, the set of couplings between F and R, I'm going to denote by curly C of F and R, and it's known to be non-empty because you have the obvious coupling F times R, which is simply you map X and psi to F of X and psi times R, and you can check immediately that that it belongs to C of F and R, right? Good, so now you want to define a classical to quantum transport cost. So now classical to quantum transport cost should be the cost of moving moving your system, moving matter from, or traveling from a point in phase space with coordinates x and psi, so x is going to be the position, and psi is going to be the momentum, to a quantum point with coordinates with position y, so y is here, fine, and momentum, well, momentum is going to be minus I h bar del y, as it should. So you look at this expression here, which makes perfect sense as a shifted harmonic oscillator in phase space, right? So it's a harmonic oscillator, but you shift the momentum variable by psi, and you shift the position by y. And there is this lambda, which is a parameter, which is going to play some role in the coming analysis, right? So you have a whole family of costs, which is parameterized by lambda. Okay, now, because this is a shifted harmonic oscillator, Heisenberg's uncertainty inequality tells you that C h bar lambda of x and psi is always bounded below by lambda d h bar times the identity. If I didn't make mistakes in the computations, I think this is okay, right? All right. So now the metric, yeah, I shamelessly call it a metric, although this is not really a metric, but okay, right? I mean, all right, so now I'm going to look at density operators, which are analogous to having second-order moments, meaning that they have finite energy when the energy is computed with the harmonic oscillator, right? So you want that the trace of square root t x squared minus Laplacian square root t is finite. And similarly, you take phase space densities such that the second order moment in phase space is finite. Okay, and then you define something which I will call a Gothic d lambda of f and r squared to be the infimum of all couplings of f and r of the integral in phase space of the trace of q of xi 1/2 times the transport cost, which is this shifted harmonic oscillator, times q of x and psi square root. And of course, this object, because of this inequality here, is always bounded below by lambda d h bar, right? So, but, you know, I mean, this is fine since anyway f and r are not going to coincide because they're different objects. The fact that this is non-zero is not a problem, okay? Good, so...
Is Q again?
Sorry?
What is Q?
What is Q? Q is a coupling. Q is a coupling of f and r. In other words, it's an operator-valued map of x and psi satisfying these, which is positive, self-adjoint, etc., and satisfying these two marginal constraints. Okay? All right. And you essentially copy the Kantorovich definition, whatever. The only thing is that because inside the trace you want a non-negative operator, it's a good idea to write it in this way rather than C times Q, because C times Q might fail, will in general not be trace class. Okay, if you write it in this way, so you should always write it in this way because now the operator inside the trace is a non-negative operator, and then you can define the trace pretty much in the same way as you define the integral of non-negative function, provided it's measurable. Okay?
So can you just ask, what exactly does psi plus IH bar nabla y mean? Does that mean that if you take the Fourier transform, it's the same as this x minus y term, or?
Yes, it's the same xi minus whatever Fourier variable of y is, right? So that's so really it's a quadratic differential operator, right? So it's you just expand. Yeah, it's a quadratic operator. Okay, good. So. All right, and with this, turns out that this, why is this Gothic d lambda going to be nice for us? Well, this is because it propagates well under classical and quantum dynamics. So now, assume that you have, so that's the result which we proved with Thierry in this paper that appeared some time ago in Archive for Rational Mechanics and Analysis. So assume that V is C11, right? So del V is Lipschitz continuous. The force field is Lipschitz continuous, right? Such that curly H is a self-adjoint extension to L2, and you denote the quantum dynamics by U of T, okay? And likewise, you consider the classical Hamiltonian corresponding to this curly H, classical, which you denote by capital H now, which is a function of x and psi. And it has a classical Hamiltonian flow, which I define to be capital phi, t, x, and psi. Right? And now, the thing is that if you pick your favorite phase space density, and your favorite initial density operator on L2, then you can compute the metric between F initial propagated by the classical mechanics and the density operator propagated by the conjugation with the Schrödinger flow. And this distance, this metric, is controlled by what it is initially, with an exponential amplification, e to the L absolute value of t, because t could be either positive or negative, and L is given, you have an inequality with L given by this form here, so 1/2 of lambda plus 1 over lambda, the Lipschitz constants of del V, okay?
This is uniform in H?
And this is, of course, uniform in H, and this is the interest of the whole business, okay? It has to be uniform in H. That's why we like it, okay? Right, so, good. So, all right, so let's see how it works. Well, the idea, there's something maybe pair dispersion is something that it's called that way in fluid mechanics, but I'm not sure it's received terminology, but roughly speaking, is that you take two trajectories of the same Hamiltonian flow. Actually, you could take two different potentials. It would be an extra term, but essentially you take two trajectories, x psi and y eta of your Hamiltonian flow, right? So they satisfy, if you look at the difference, satisfy this differential identity here. And now you compute d by dt of the Euclidean norm of x psi minus y eta, and this Euclidean norm with this parameter lambda squared, right? So you have d by dt of lambda square x minus y square plus psi minus eta square, and then you compute it, right? Okay, so here Cauchy-Schwarz. This is very easy computation. Here Cauchy-Schwarz, good. Here we know that del v minus at x minus del v at y, you control it by the Lipschitz condition. You divide the Lipschitz constant by lambda, you multiply by lambda here, you apply something which I think in this country goes by the name, the Peter Paul inequality. Here's what you get, okay? Good. All right, this is fairly simple. This is a case where you compare two trajectories, two classical trajectories. Now, what is this going to do in the case where you're comparing a classical trajectory and a quantum, I should not say trajectory, but a quantum, whatever. Yeah, well, you see what I mean. I found this interesting observation, which I never could find in any classical textbook, but it's in this paper. It goes by the name of the Drei-Männer-Arbeit from the very beginning of quantum mechanics. So by the Born, Heisenberg, and Jordan, 1926. So the idea is that if you look at the position and momentum operators, say in space dimension 1, and you look at the quantum Hamiltonian defined in this way, and what you do is you define you propagate Q, the position operator, by conjugation with the Schrödinger group, P likewise, gives you a Q of T and a P of T. And what these gentlemen observed is that these operators that satisfy this beautiful equation here, which is the same equation as in classical mechanics. So in other words, this supports this idea that quantum and classical dynamics, they are the same, but they operate on different objects, right? So good. So then the idea is that you return to this inequality here, which is an inequality between numbers, and then you replace y and eta by by q of t and p of t in the pair dispersion inequality, and you have an inequality between operators that you can check pretty much in a standard manner. So with this, yeah, well, how am I doing with respect to time? What am I supposed to finish?
Slightly over 10 minutes. That one is slow.
Yeah, okay.
So you have
Yeah, all right, so, okay, so essentially the idea is that you enter this information inside the definition of the distance. The distance is always bounded by, so you pick your favorite coupling, right? And then essentially taking time derivatives on the couplings by integration by parts and by the analogous of integration by parts under the trace amounts to computing the Poisson bracket of the classical Hamiltonian with your with the variables x and psi in the cost, and computing the commutator of the quantum Hamiltonian with c viewed as an operator in y. Right, and when you do this, then you apply the simple inequality which I showed you, and you get pretty much the inequality immediately. What am I doing? Oh yeah. Wait a minute. I'm hitting the wrong button. So, and pretty much you arrive in a straightforward manner to this inequality here. Okay. Now, how is this going to help us? Well, the thing is that now the idea is that we're going to get an observation constant by using this optimal transport argument. We're going to get an observation constant that's going to be a correction, a quantum correction to the classical observation constant, which comes out from the Bardous-Le Bourroche condition. Now, the observation constant is not explicit, but admittedly, if you know the classical dynamics, then you have all means to compute it. And here, I'm just going to tell you that it exists. I mean, there's some observability constant, classical one, that exists, and there you understand why I took K to be compact, omega open set, omega to be open, and T positive, because now, under the geometry condition, do I need to remind it? So, you know, I mean, there is one time between 0 and capital T where any trajectory starting from K is going to enter the observation domain omega, right? Okay, so with this, what I'm saying is that if I take the infimum over all phase space points in capital K of the integral between 0 and capital T of the indicator that x is in omega, dt, well, this is positive, right? This is always a positive number. And the argument is that because omega is open, this guy under the integral is going to be lower semi-continuous. You know that there will be, by the geometry condition, some time between 0 and capital T, depending on x and psi, for which this is going to be equal to 1, right? So therefore, the integral is for each x and psi in the compact set positive, and by Fatou lemma, the positive function with the integral is going to be lower semi-continuous on K, which is compact, and therefore it attains its minimum on K, right? So that's sort of abstract nonsense topological, but if you want to compute it, then you have to roll up your sleeves and compute the dynamics, of course. Okay, but assume that you have these C, K, omega T, which you have computed by solving the classical trajectories. Now, what I'm saying is that under the same conditions as before, then you get you're going to get, provided that your K, omega, and T satisfy the geometry condition, then you get a observation constant, which is going to be at least the geometric constant, which I've not computed, but which I've defined, which is a positive number, right, minus something, which is going to be a semi-classical correction. And this semi-classical correction I can compute explicitly, I mean relatively explicitly. So it depends first on a parameter delta, which boils down to enlarging a little bit the region of control or the region of observation. You enlarge it by a distance delta, right? And here I have some thing which comes from the Grunwald inequality in the propagation of the Wasserstein distance. So you recognize the function exponential of t times the Lipschitz constant, etc., minus 1 divided by the Lipschitz constant. I mean, the usual stuff. And here you have the infimum of the distance from R initial to your favorite classical phase space density supported in K, right? So you take the infimum of this. So this is, I mean, this is you can think of this as a semi-classical correction in the sense that if your initial data, R initial, is well approximated by phase space probability densities in the sense of this metric, then this can be made arbitrarily small, at least as the semi-classical parameter tends to 0. But now I want to insist that here, I don't want this guy to actually tend to 0. It suffices that this quantity here, which is a number, be below this quantity here, which is a number which is independent of h bar, right? That's it's like, I mean, this could be, I don't know, this could be 1/10. And if you want to have an observation constant, all you need is that this semi-classical correction be less than 1/10, right? It doesn't have to be, you don't have to take h bar going to 0, right? So it's, you really have thresholds if you want, right? Oh, okay, so I can do it in this way. Now let's check how this is going to work on two different classes of initial data. So here I can take a convex combination of coherent states, right? So I take exponential wave packets, like the Gaussian wave packets like this, and I take the superposition of Gaussian wave packets with some probability density. In that case, you can check that this d lambda, Gothic d lambda between f initial and r initial, that tells you how f initial is going to approximate your quantum density, is controlled by the Wasserstein, the classical Wasserstein distance between the classical density and the measure which you put in the definition of r initial here, which should be mu initial, sorry, plus lambda dh bar, right? And it's bounded below by lambda dh bar. So that if you assume that the support of your measure is inside K, then the infimum of this guy here is precisely equal to the square root of lambda dh bar. And then your observation constant, 1 over your observation constant, according to this formula here, right? According to this formula here, your observation constant is going to be the classical observation constant minus something which you can compute by kindergarten analysis. Well, now kindergarten, advanced kindergarten analysis, but I mean, they give you something which is fairly explicit in terms of lambda and delta, and voila. Okay, that's one first example of initial data for which you can get an observation constant. Let me look at the case of a pure state. So here it's a little less pretty. Oops, I did something wrong with the tag here. Okay, so here you're going to take the Usimi function of your initial state, psi initial. So psi initial is going to be an initial wave function, right? And so your observation constant is going to be the geometric constant times the integral of your Usimi function of your initial wave function inside K. Now, this is going to be slightly less than 1, not good because you want this as large as possible, but you reduce a little bit. This is life, okay? And then you have this classical correction, which involves this explicit function here, right? Where again, some obvious Grunwald type object, and the dispersion of your psi initial, I mean the quantity that appears in the Heisenberg inequality, right? So that's the variance in position and in momentum of psi initial. Okay, so you have fairly obvious computations giving you observation constants. Now, just one word of the proof. The idea is that, of course, you want to, where is it? So you want to control, you want to estimate this quantity here. And the idea is that you are going to estimate this quantity by this classical analog, right? And this will control the semi-classical correction, which is here. And to do this, where is it? Geez, I don't know how to, yeah, here it is. So, so here, the quantity that you want to control, so you're going to replace the indicator that you are inside the region of control by chi, which is a smooth version thereof. Right? And you look at a trace of chi times r of t minus the analogous quantity, but in the classical setting, involving some approximation f of your r of t, which is generated by taking the initial phase space function and you propagate it by the classical flow. And the thing is that if you look at this difference here, right, so you can feel everything inside an integral. And here you observe that you have a Lipschitz condition on chi, which enters and which you can immediately control by this quantum Wasserstein distance. And then you use the probability, you use the propagation theorem for this quantum Wasserstein, and it gives you the result. Okay, so that's how it works. Okay, so to conclude, so here, with this, we proved an observation inequality for quantum dynamics. It uses the only assumption that V is regular enough for the existence of uniqueness of the classical dynamics. In other words, you need just C11 potential. So this is the only information you need to be able to define trajectories by Cauchy-Lipschitz, right? So whereas probably microlocal techniques would require more regularity. Typically, because you need parametrizes and all that, so you need more regularity. So here, the observation constant is explicit in terms of the geometric data, the Bardos-Lobo-Rausch controllability condition, provided, of course, that you can compute the observation constant for the classical problem. And yeah, I mean, the approach involves this quantum analog of the Wasserstein distance between classical and quantum densities. Now, it would be probably interesting to obtain a controllability statement by some duality argument, like in the Hilbert uniqueness method. Would be probably interesting also to include magnetic fields. I understand there's been this has been partially done in the PhD thesis of Emmanuel Ben-Porat, a former PhD student of mine, and why not try other dispersive dynamics, maybe less interesting for the quantum mechanics. I don't know. I mean, Klein-Gordon being an example. I don't know. Okay, thank you very much.